Yes, welcome to the third lecture of the course operating system. So in this lecture, we'll be basically discussing three concepts. The first thing we'll be discussing is the storage structure in a computer system. And then we'll be discussing about cache memory. And then we'll be discussing about a concept called direct memory access. Okay. So we'll start with storage structures. But before exactly discussing about storage structures, we'll try to understand certain important definitions and notations in the context of storage. So here storage, in the sense, we refer to two types of storage. One is a primary storage, the other one is a secondary storage. The primary storage is volatile in nature. That is, the data will be available in a primary storage device only as long as power is available. The moment you remove the power, the data will be lost. Okay. But these storage devices will be very fast to access, and they will be closer to the processor, that is CPU. Okay. So these are the features of a primary storage device. The primary storage devices are volatile in nature, in the sense the data will be available only as long as the power will be available. But the accessing speed of these devices will be very fast, and physically also they will be located close to the processor. So the processor can access the data that is stored in a primary storage device at a very faster rate. So with respect to the processor, this is the primary memory or main memory. So they are called as primary storage devices. Okay. But when you come to the secondary storage devices, the secondary storage devices are non-volatile in nature. That is, the data will be available in the secondary storage even if the power is not available. Okay. But the accessibility speed of these devices will not be that fast as that of the primary storage device. It will be very much slower, and also it will be located physically also away from the CPU, central processing unit. So with respect to the processor, this is a secondary storage. Okay. So in that context, it is called as a secondary storage device. A typical example for primary storage device is RAM, random access memory, and a typical example for secondary storage device is hard disks or CD disks, okay, compact disks, all such things. Okay, fine. So with this understanding, let us move into the storage definitions and notations. The basic unit of storage in a computer system is called as bit. Okay, this is the basic unit of storage in a computer system. A bit can hold two possible values. Either it can be 1 or it can be 0. So 1 represents something is on and 0 represents something is off. And a collection of 8 bits is called as byte. A collection of 8 bits is called as a byte. And a collection of 1024 bits is called as 1 kilobyte. And 1024 kilobytes is called as 1 megabyte. And 1024 megabytes is called as 1. And 1024 gigabyte is called as 1 terabyte. And 1024 terabyte is called as 1 petabyte. It goes on like this. There is no stop in this. Okay, it goes on like this. So technically or academically, we say that 1024 byte is 1 kilobyte, 1024 kilobyte is 1 megabyte, and 1024 megabyte is 1 gigabyte, like that. But in commercial aspect, this 1024 is rounded off to 1000. So if you meet any commercial vendors, their language will be a little different, and they will be considering 1000 byte as 1 kilobyte, and 1000 kilobyte as 1 megabyte, and 1000 megabyte as 1 gigabyte. and 1000 gigabyte as 1 terabyte and so on. Okay. There is another terminology with respect to storage, and that is called as word. And the size of a word varies with respect to the type of the computer. If the computer uses a 64-bit register and if it uses 64-bit uh, memory addressing scheme, then the word size of the computer is called as then it is called as a 64-bit word computer. Okay. If the computer uses 64-bit registers and 64-bit for memory addressing, then such a computer is said to be a 64-bit computer. Okay. But if a computer uses 32-bit register and if it uses 32-bit memory addressing scheme, then the word size of that particular computer will be 32 bits. Okay. If a computer uses 16-bit registers and if it uses 16-bit addressing scheme for referring to the memory, then the word size of that computer is 16 bits. Okay. So the size of the word is not constant. The size of the word is actually decided by the register size and the memory addressing scheme. Okay. Whereas these sizes are constant. Bit, there is no change in byte. A byte is always 8 bits. A kilobyte is always 1024 bits. Of course, in commercial angle, 1000 bytes is called as 1 kilobyte. That is different. Okay. And 1024 kilobyte is 1 megabyte and 1024 megabyte is in 1 gigabyte. But that is not the case with word. In some computer, the word size may be 32 bit. It means it uses 32-bit registers and it uses 32-bit addressing to refer to memory. In some other computer, the word size may be 64-bit. It means it uses 64-bit registers and it uses 64-bit addressing scheme to refer to memory. Okay. So this is what word means, right? So having understood these basic definitions and notations with respect to storage, now let us go to the storage structure. So let us try to understand the storage structure with this particular diagram. Okay. So this is the storage hierarchy. This is the storage hierarchy. At the bottom, you can see we have magnetic tapes. This is one type of storage. Okay. And then you have optical disc. So optical discs include CDs, DVDs, okay, compact discs, DVDs, all these things. And then we have hard disks. And then we have solid state discs. So all these up to solid state, from solid state disk to magnetic disk, all these are secondary storage devices. Okay. So what is a secondary storage device? They are non-volatile. Okay. So I will call as NV. They are non-volatile. That is, the data that is stored in these devices are permanent. The data stored in these devices will not be removed when the power is not available. Okay. But comparatively, they are the accessing speed of these devices were slow when compared to the primary storage device. Okay. And the cost, the unit cost of these devices are also comparatively cheap when compared with the primary storage device. Okay. So these are the core features of a secondary storage device. Okay. After solid state disks, what you have is a main memory. So main memory refers to RAM, random access memory. And then we have cache memory, CACHE, cache memory. So what is cache memory? All this we'll discuss later. So as of now, you can understand that a cache memory is a high speed memory. A cache memory is a high speed memory which is placed in between processor and main memory. So you can assume that processor is there and then main memory is there. Somewhere in between these two, there will be another high speed memory, and that high speed memory is called as cache memory. Okay. Actually, there are two types of cache memory. One is an internal cache, the other one is an external cache. This internal cache will be placed inside the processor itself, and the external cache memory will be placed outside the processor in between the main memory and the central processing unit. And then we have registers. Registers are special memory locations which are inside the processor, inside the central processing unit. Okay, so all these three registers, cache memory, main memory, these are the primary storage devices. Okay, so these are what these, so these are called as primary storage devices. Okay, so why it is called as primary storage device? Because when any data, if CPU wants any data, first it will check register, it will check the registers. If the data is not available in the registers, then it will check cache memory. If still the data is not available, then it will check the main memory. So with respect to the processor, these are the primary memory. Okay, so it is called as primary storage device, and these are volatile in nature. That is, the data will be available in these devices as long as power is available. If the power is removed from this device, then the data will also will get lost. Okay, and these are high speed devices. Okay, that is, the processor can access this memory in a very less time. So here also there is a hierarchy. The registers, or the processor can access the register very fastly than it access the cache memory. Similarly, the processor can access cache memory relatively at a higher speed than it accesses the main memory. Okay, so not only with respect to devices, not only with respect to the distance, but also the type of material with which they are formed. Because of that, they are easy and free to access at a greater speed, and the cost of these memory are high. The cost of these memory are high. Okay, whereas the cost of unit cost of this memory is very high when compared to secondary storage device. Here also, if you see, the cost of main memory, the unit cost of main memory will be comparatively lesser than the unit cost of cache memory, and the unit cost of cache memory will be comparatively lesser than the unit cost of registers. Okay, as the cost is less, the size of these memory also will, sorry, as the cost is more, the size of these memory will also be less. Okay, because a typical user cannot afford uh, for a for a huge size of register by paying lot of money. Okay, so the size of these memory will be small as it is high cost. Okay, so the point I uh, want you to understand in this sense, there are three things which you should be clear. One is speed, cost, and volatility. Okay, so volatile in the sense they are temporary. That is, the memory, the data will be available in the memory as long as the power is available. Non-volatile in the sense the data will be available irrespective of whether the power is available or not. Okay, so if you see, the speed of these devices increase in this direction. Okay, so speed increases in this direction. Okay, so the magnetic disks are the slowest devices, and then comes optical disk, which is comparatively faster than magnetic tapes, and then hard disks. Hard disks are faster than optical disk, and then solid state disk. Solid state disks are more faster than hard disk. So I would like to spend some time in solid state disk. So what is a solid state disk? So solid state disks are specific, are flash disks. Okay, so they are made up of flash memory, whereas hard disk is made up of magnetic material. Hard disk is made up of magnetic material. So hard disk will have some spinning mechanism. So basically it contains several cylinders. Hard disk contains several cylinders, and there will be a head, and these cylinders will be rotating, and the head will be moving back and forth, and the cylinder will be divided into several tracks and sectors, and this is how the data is accessed from the hard disk. So the probability of a hard disk, the failure probability of hard disk is quite high, because the failure probability of the hard disk is quite high, The reason is this is because it contains moving parts. So for the more the parts move, there is more chance for the parts to get damaged. Okay, and then whereas solid state disks are basically flash memory, there is no movable parts in these devices, and they are also very compact in nature. It can be slided over the PCI slots or some other slots which are available in the computer. So these are quite new forms of secondary storage device which is available in the market. Okay, so the speed increases in this direction. So the main memory will be it is the processor can access the main memory at a higher speed than it can access the solid state disk. Similarly, processor can access the cache at a greater speed than how it can access the main memory, and processor can access registers with utmost speed. Okay, so speed increases this way. Okay, so let me call it as SP. Speed increases this way. Okay, cost. So the second thing is cost. What about cost? Yeah, cost also increases this way. Cost also increases this way. So let me call it as CST, cost. So the unit cost of registers is high when compared to the unit cost of cache. The unit cost of cache is higher when compared to main memory. So the unit cost of magnetic tape is very less, so that you can have a huge magnetic tape. Okay, a typical user normally will not have a magnetic tapes, but normally in industries there will be magnetic tape for storing backup contents. Okay, so optical discs or what do you call, or the cost is also, its cost is also less. Okay, but the unit cost of optical disc is higher, comparatively higher than magnetic tapes. Okay, and the unit cost of hard disk is comparatively higher than optical disk. Okay, so the cost also increases this way. So as you go up the hierarchy, the cost keeps increasing. As the cost keeps increasing, you cannot afford to have a huge memory. So that is the reason the size is decreasing. Okay, and then comes volatility. Okay, so which is more volatile and which is less volatile. Again volatility also goes in this direction. Okay, so if you, so this is, so magnetic tapes are less volatile, whereas registers are highly volatile. All these three are basically volatile. Okay, these three are volatile, that is registers, cache and main memory. That is, the content will be available only as long as the power is available. Whereas solid state, hard disks, optical disk and magnetic tapes, these are non-volatile. That is, the content will be available irrespective of the, what you call, the power is available or not. Okay. So with these three parameters, we can, I think, understand the nature of these devices. Okay. So I can draw another line in this direction with respect to the size. So size of the devices. So size of the devices typically increases this way. Okay. So if you see, so the size of the registers is very small, whereas the size of the magnetic tape is very high. Okay. So that is the basic understanding about storage device hierarchy. Fine. So this is the overview of it. I hope you have understood. So now let us discuss about cache memory. What is a cache memory? As I have already told you, cache memory is a high speed memory. Cache memory is a high speed memory which is placed in between processor, that is central processing unit, and the main memory. Okay. So when the CPU wants some data, if the CPU wants some data, first it will check whether the data is available in the register or not. Okay, if the data is available in the register, the CPU will take the data from the register and it will use that data, right? That's it, nothing else. If the data is not available in the register, then what the CPU will do in the sense, the CPU will check whether the data is available in the cache memory or not. If the data is available in the cache memory, then it will take. Otherwise, it will go and check the main memory, whether the data is available in the main memory or not. If the data is available in the main memory, it will use it. The data is not available in the main memory, then it will check uh, either the solid state disk or the hard disk, depending on the nature of your computer. If your computer uses solid state disk, then it will check the solid state disk. Otherwise, it will check the hard disk whether the data is here or not. If it is here, if it is there in any one of the device, it will use. Otherwise, it won't. Otherwise, it means it will go and take the if the data is in the main memory, the processor will take the data. Otherwise, it has to retrieve the data from the hard disk. Okay. So this is how data is accessed from the storage devices, right? So now let us see. Assume that the computer is trying to load some program from hard disk. Okay. So let us assume my computer has a hard disk. So the computer loads that program from hard disk to main memory. Okay, it keeps the program in the main memory, right? Let us assume the size of the program is, 1 GB. Okay, the size of the program it is loading is 1 GB. Okay, fine. But let us also assume that my memory capacity, the RAM capacity is also 1 GB. My system RAM capacity is also 1 GB. That is, it cannot hold more than 1 GB of data. As you already know, some part of memory will be used for storing some operating system related things, some interrupt service routine. So even though you have 1 GB memory space, the CPU cannot give the entire 1 GB memory space for some program. Okay, because some part of the hard disk has to be used by operating system related routines will be always stored in some part of the hard disk. So leaving that, let us assume that the free space available in the main memory is 600 MB. Okay, let us assume this free space available is 600 MB. Okay, so if the free space is 600 MB, but the program, the processor is trying to access is 1 GB. So it means it cannot access the entire program. It can only access the part of the program. So it will not access the full 1 GB content. It will just access the 600 MB of that particular program, which the operating system thinks as the important part of the program. So that 600 MB content alone will be moved to main memory. Okay, is it clear? Now let us assume that the cache memory size is, 100 MB. Let us assume that cache memory size is 100 MB. Now what the processor will do in the sense, from this 600 MB, from the 600 MB of content which is loaded from the hard disk to the main memory, the operating system will try to understand which is the 100 MB which is more important. So that 100 MB, that more important content 100 MB, that will be stored in cache memory. Okay, that will be stored in cache memory. Okay, fine. So that important 100 MB content will be stored in cache memory. Okay, from cache memory, let us assume that there are some 4, 5 or 10 important data items that the CPU access very frequently. So now what the operating system will do in the sense, it will move those 10 data items to the registers. Okay, so I think you got the point. Actual program which the operating system wants to load is 1 GB memory. but we don't have that much memory in the RAM. The entire memory capacity is 1 GB and the free memory that we have is 600 MB. So operating system cannot load the entire 1 GB, rather it just loads the 600 MB of content which it feels is important. Okay. Again, from this 600 MB, it will move the most frequently accessed 100 MB contents to cache. Again, from this 100 MB, it will move some 10 data items which are most frequently used by CPU to registers. Okay. Now, when CPU requests for any new data item, any new data from this particular program, what the operating system will do in the sense, operating system will first check the register, whether the data is available in any one of these 10 registers or not. If the data is available, it will give it to the CPU. If it is not available, then it will come to the cache and it will check. Out of this 100 MB, is it available or not? Whatever the data is requested by the CPU. If it is not available, if it is available, it will fetch from the cache memory and it will be given to the CPU. That is what the operating system will do. If it is not available in the cache memory, then the operating system will go and check in the main memory. Out of this 600 memory, is the data item that is requested by the CPU is available somewhere in the 600 MB of content or not. If it is available, then it will fetch that particular content and it will give to the CPU. If it is not available, then it means that it is not in the main memory, rather it is in the hard disk. Because from hard disk we moved only 600 MB, there is another 400 MB. Okay, so it will go back and check the hard disk and it will identify from which part of the 400 MB it is available. Okay, are you getting? So say somewhere some part of the say somewhere it is available in that 400 MB at some part, say from at location 201 MB it is available, then that particular data it will fetch and it will keep it in the main memory. Okay, and then the CPU can access. Okay, so this is how memory works. So in this context, what you can see in the sense, even though we define cache memory as, how we define cache memory is a high speed memory. Cache memory is a high speed memory which is placed in between main memory and the CPU. Okay, cache memory is a high speed memory which is placed in between main memory and the central processing unit. Okay, but you can also say that main memory is a cache memory with respect to hard disk and the cache memory, because if you see, main memory is placed between hard disks and cache memory. Okay, in this case main memory is acting as a cache, so every level there is a cache. Okay, at every level also you can say there is a cache memory available. Okay. I hope you understand what I'm trying to say. So the general definition of cache memory is a high speed memory that is placed in between the main memory and the CPU, but still you can say that main memory is a cache memory with respect to the hard disk. Okay, cache memory is a cache memory with respect to main memory. The actual cache memory is a cache memory with respect to main memory and CPU. Okay, with respect to hard disk and the cache memory, main memory is a cache memory. Okay, so that is what I'm trying to say. Okay. So this is how the storage hierarchy works in a typical computer. I guess you have understood. Okay, so whatever we have discussed, that is what is being explained in this slide. So when any data is required, first the computer or the CPU will look into it will first look into the faster storage device. Okay, and if the data is not available in the faster storage device, then it will go to the next level of slower storage device to check whether it is available or not. So first the fastest storage device is register. So the CPU will first check register whether the data is available or not. If it is available in the register, it will take and use. If it is not available, then it will go and check the cache memory. If it is not available in the cache memory, then it will go to the main memory. If it is available in the main memory, it will take and use. Otherwise, it will go to the secondary storage device. Okay. So this is how the data or get accessed in a from a storage from storage devices. Okay. So that's it about storage hierarchy and caching. Next, we'll be discussing about an important concept called as direct memory access. Okay, so what does it mean? So what does it mean by direct memory access? See, typically, if any device would like to access the main memory, so device in the sense here we represent some hardware device. It may be a hard disk drive. Okay, I mean the hard disk drive in the sense hard disk drive controller. It may be a hard disk drive controller. It may be a graphics adapter. It may be a network adapter. Okay, if any of these devices wanted to access the main memory, they normally they cannot access directly. They will get it accessed through the processor. They will get it accessed through the processor. So first they will create an interrupt to the processor. That is, they will send this particular device will send a signal to the processor that we want to access main memory to read this much amount of data or to write this much amount of data. Like that they will place a request. Okay. Then the CPU will, then actually that particular job will be done by the CPU. Okay. So this is how a typical memory accessing works. So you can see this diagram. So this part, so this particular part, this is nothing but CPU. So this is your CPU, central processing unit, and this is a device, hardware device. It can be a hard disk controller, which I am calling it as HDC, or it can be a graphics controller or graphics adapter. Okay, or it can be a network interface card or network controller, NC. Okay, so it can be any device. Okay, if any of these device want to access the main memory, so this is the main memory, RAM. Okay, so if any of these devices would like to access the main memory, then normally how it works in the sense, these devices will send a will send a signal to the processor. That is, it will send an interrupt. It will create an interrupt by sending a signal. So the interrupt says, so what this interrupt says in the sense, we need to access main memory for performing some operation. Okay, so let us say that this is a graphics adapter and it wants to write something to main memory. It wants to write something to main memory. Then after creating the interrupt, then what it will do in the sense, so the processor, so you know, whenever there is an interrupt, the interrupt service routine will execute so that the job will be completed. Okay, that is what we discussed in the last class. So here what the interrupt service routine will do in the sense, the interrupt service routine, what it will do in the sense, it will check what type of operation it want to perform. So it can perform two operations. It can perform either a read operation or it can perform a write operation. Okay, so now there are two possible operations are available. One is a read operation, the other one is a write operation. Read operation in the sense, reading some data from the device and storing it in the main memory. Okay, read means read some data from the particular device. If it is a graphics adapter, read the data from the graphics adapter and store it in the main memory. Write in the sense, read some data from main memory and store it in the device. So whether it is read or write is with respect to the device. Okay, So whether it is read or write, that information will be available in this IO request signal. In this IO request signal, it will be whether read or write. Okay. So now let us assume this is an interrupt is generated and the interrupt service routine, then it will immediately check this IO request, whether it is read or write. Let us assume it is write. So it is write means then some data should be moved from main memory and it should be returned to the device. So the CPU will read the appropriate data from the main memory and it will write it to the device. Okay, so this is how it works. If it is a read operation, then once the interrupt is created, the interrupt service routine first it will check whether what operation it is. It is a read operation. Now what the CPU will do in the sense, CPU will read some data from the device and it will write that data to the main memory. Okay, so basically all these tasks were done by CPU. Okay, the device only just creates an interrupt and it says whether it is a read operation or a write operation through this particular signal. Okay, so this read and write operation also includes from which memory location it should be written or from which memory location it should be read. All these information will be available here. Okay, accordingly the CPU will do the job, and once the job is done, the particular interrupt is serviced. Okay, so this is how normally data is transferred from a device to a memory or from a memory to a device. Okay, but this type of data transfer happens only for transferring small amount of data. But this type of data transfer happens only for transferring small amount of data, say for transferring 1 byte of data. So if you want to transfer 1 byte of data, then this kind of things will work. That is, whenever the device wants to transfer 1 byte of data either from device to memory or from memory to device, things works this way. They will create an interrupt and then the CPU will take charge and the CPU will transfer the data from either device to the memory or from memory to the device. But say that you want to perform, the device want to perform block transfer. Let's say that the device want to perform block transfer. So what is meant by block transfer? So block transfer in the sense, it want to perform a block of data. A block is nothing but a collection of bytes. A block is nothing but a collection of bytes. So the size of the block varies. It depends. Okay, so let us assume that one block is equal to, let us assume that one block, I'll call it BLCK. Okay, so let us assume that one block is equal to 10 bytes. Okay, so one block is equal to 10 bytes. This is what my understanding, right? So now let us see how this will work. So this is C. Okay. So one block is equal to 10 bytes. So how this will work in the sense, now let us assume that the device want to transfer 2 blocks. The device want to transfer 2 blocks of data to main memory. Okay. So one block is 10 bytes. So 2 block is 20 bytes. Okay. So now it will not use the normal data transfer feature, which is done by the CPU. Rather, it uses a technique called DMA, direct memory access. Rather, it uses a technique called DMA, which means that direct memory access. So in direct memory access, what happens in the sense, the device can access the main memory without the involvement of CPU. In a normal data transfer, for transferring small amount of data, the device cannot transfer directly. The data will be transferred actually by the CPU, central processing unit. But here what happens in the sense, when you want to transfer a block of data, the device actually can perform the data transfer without involving the central processing unit. So how it does in the sense, so whenever the device want to transfer a block of data, So here the device want to transfer 2 blocks of data. Okay. So what it will do in the sense, it will give one interrupt to the CPU stating that I am going to transfer a block of data. Okay. So the device gives a signal to the CPU stating that I am going to transfer a block of data to the main memory. Okay. So the data can be transferred either from device to memory or from memory to device. That depends on what type of operation it is, whether it is a read or write. If it is a read operation, the data will be moved from device to memory. If it is a write operation, the data will be moved from memory to the device. Okay, it depends, right? So it will first generate a interrupt to the processor stating that I'm going to perform a block transfer. So the CPU will understand that. The device, some device is going to use the system bus for accessing the main memory. What is a bus? See, bus is a communication channel to access the main memory. Bus is nothing but a communication channel to access the main memory. Okay. And in a normal computer, there will be only one bus available. So only one device can use the bus. If CPU is using the bus, then some other device cannot use the bus. If some other device is using the bus, then CPU cannot use the bus. Okay. So I will try to draw here. See, this is, say, assume this is the memory. Okay, main memory. I'm calling it as M. Okay. And here we have, say, CPU. I'll call it as C. And then say we have hard disk controller. I'll call it as H. Okay. And then we have, say, graphics adapter. I'll call it as G. So all these are connected like this. Okay. And what is this? This is nothing but system bus. This is the communication channel. I'll call this as SB, system bus. So if any of these devices want to access the main memory, they should access through this system bus. Without the system bus, they cannot access the main memory. So system bus is very important thing, and it is a shared bus. Okay, you can see here there is a shared bus. So this communication channel is called as bus. So only one device can use the bus at a given point of time. If CPU is using the bus, if CPU is using the bus, then hard disk controller should not use. If hard disk controller is using, then graphics controller should not use. Okay. So before using the bus, you should check whether the bus is free or not. Only if the bus is free, somebody else can use that. Okay. So that is the reason why the device. So here we are assuming the device as graphics controller. Okay. So the graphics controller, before performing the block transfer, what it does is it first sends a signal to the CPU. So this signal says that I am going to perform a block transfer, which means that I am going to use the system bus. So after giving the signal to the CPU, the graphics controller will take control of the system bus. It will take control of the system bus. Now system bus is in the control of graphics controller, and it will perform a block transfer of 10 bytes of data. That is, it will continuously move 10 bytes of data from device to memory or from memory to device. Okay. Once one block of data was transmitted, once 10 byte of data is getting transmitted, then it will again inform to the CPU through another interrupt. It will say that I have finished transferring one block of data. But actually the device should transfer 2 blocks, not 1 blocks. So there is another block of data left. So again the device will create an interrupt to the CPU. Okay, again the device will create an interrupt to the CPU that once again I need the system bus because I need to transfer one more block of data. Okay. If the system bus is not being used by CPU, then obviously the graphics controller will get access to the system bus. Otherwise, it may have to wait for some time. Once the system bus is free, the graphics controller will get the system bus, and once it got the system bus, again it will start transferring another block of data, which is another 10 bytes. Okay, so this type of memory access, where the memory can be accessed by any hardware device without the direct involvement of central processing unit, is called as DMA, direct memory access. Okay, so what is the advantage of direct memory access? The advantage of direct memory access is, say for example, for performing one block of data transfer, it takes 20 seconds for the device to perform one block of data transfer, that is for to perform 10 bytes of data transfer. Then during this 20 seconds we are not using the CPU, that is graphics controller is not using the CPU. So it means that CPU can be used for some other computation. So it means that CPU can be used for some other computation. Okay, so we are not holding on the CPU, so that is the advantage. Okay, so 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 the point here is, if the data transfer is for if you want to perform small amount of data transfer like 1 byte or 2 byte, then normally such data transfer will be performed through the central processing unit or by the central processing unit. But when any device want to perform bulk data transfer, then a typical modern computer uses a technique called direct memory access, by which the device can transfer a block of data to the main memory directly without the involvement of CPU. Okay, for every block of for performing every block of data transfer, it will generate an interrupt to the processor stating that I'm going to perform a block data transfer and I need the system bus. If the system bus is free, it will take the system bus and it will perform the data transfer of one block of data, and once that is done, it will again give a signal to the CPU that I have done with one block of data transfer. Okay, so this is how it works. So say for example, if this particular device want to access 10 blocks of want to move 10 blocks of data from device to the main memory, then how it works? Then 10 times it has to create an interrupt to the CPU. Okay, that is, first time it will create an interrupt and will transfer one block of data, and then it will say I have completed one block. Then second time it will create an interrupt and it will transfer another block of data, then it will say I have completed that. Like that it will proceed. Okay, so this type of uh, um, methodology or accessing memory is called as direct memory access. Okay, so fine, let us stop here. Uh, let us stop today's session with this. So to summarize what we have discussed in the sense, so we have discussed about the storage hierarchy. Okay, so before that we have discussed about certain terminology with respect to storage. So a basic unit of storage in a computer is called as a bit, and a bit can hold a value either 1 or 0. 1 represents on and 0 represents off, and 1024 and 8 bits forms 1 byte, and 1024 byte forms 1 kilobyte. 1024 kilobyte is 1 megabyte. 1024 megabyte is 1 gigabyte. 1024 gigabyte is 1 terabyte. It goes on. Okay, so academically we use the term as 1024 byte is 1 kilobyte, or 1024 kilobyte is 1 megabyte. But in commercial context, the 24 is ignored. In commercial angle, 1000 byte is called as 1 kilobyte, and 1000 kilobyte is called as 1 megabyte, and 1000 megabyte is called as 1 gigabyte. It goes that way. Okay, so coming to the memory or storage hierarchy, at the lowest level we have magnetic tapes, then we have compact discs, then we have hard disk drives, then we have solid state disks, and then we have main memory, and then we have cache memory, and then we have registers. Okay, so when you go from bottom to the top, when you move from bottom to the top, the cost increases from bottom to the top. Okay, that is the cost of the unit cost of a magnetic tape will be very cheaper when compared to the unit cost of a register. The register's memory will be very costly. So you cannot afford for a larger space of register or a larger space of cache memory or a larger space of main memory, whereas you can go for a larger space of magnetic tapes or a larger space for hard disks or a larger space for solid state disks. Okay, and main memory, cache memory, and registers, all these are volatile in nature. That is, data will be available in these devices only as long as power is available. If power is removed, the data will be lost. Whereas the other memories, the memories or the storage devices which are available in the lower level, like solid state disks, hard disks, CDs, compact disks, and what you call uh, the magnetic tapes, all these are called as non-volatile. That is, the data available in these devices will be available even if the power is not available. So they are also called as permanent storage devices. Okay, but main memory, cache memory, and registers are called as primary storage devices, because with respect to CPU, these are the primary memory. Okay, whereas the non-volatile memory, hard disks and magnetic tapes, are the secondary storage devices with respect to the main memory. Okay, so that is with respect to cost and volatility, and also with respect to the size. So what is cache memory? Cache memory is a high speed memory which is placed in between main memory and the processor, central processing unit. Okay, so what happens in the sense, whatever the frequently accessed data from the main memory, that will be stored in the cache memory, and what are more frequently accessed, that will be stored in the register. So when CPU wants some data, first it will check the register whether the data is in the register or not. If the data is available in any of the registers, it will use it. Otherwise, it will come and check the cache memory. If data is available in the cache memory, it will take and use it. If it is not available, then it will go back to the main memory. If the data is available in the main memory, it will fetch and use it. If it is not available in the main memory, it will go back to the secondary storage device like hard disk or solid state disk, and it will access it. Okay, so this is how the storage hierarchy works. So generally, cache memory is a memory which is placed between the main memory and the central processing unit. Okay. But you can also say that main memory itself has a cache memory when you consider the context of hard disks and cache memory. Okay, for cache memory and hard disk, main memory is a cache. Okay, so you can have several levels of cache. So there are like two levels of cache, cache 1, cache 2 available in some of the computers, where level 1 cache 1 memory will be available within the CPU. Cache 2, level 2 cache will be available outside the CPU. Okay. And then at last we have discussed about direct memory access. So normally when a device want to transfer data to or from the main memory, they will do so with the help of the CPU. That is, they will generate an interrupt, and actually CPU will perform the data transfer. This is how things work. But that is not the case when the device want to perform a bulk data transfer. So if a device want to perform 2 blocks of data, so the size of a block may vary with respect to the type of the computer organization. So here we assume that one block is equal to 10 bytes. So in that case, for every 1 byte, it will not use the CPU. Rather, for transferring one block, it will just give a signal to the CPU, and it will directly access the memory, and it will move the content either from device to memory or from memory to device. Okay, so this concept of an operating system to directly move data from device to memory or memory to device is called as DMA, direct memory access. Okay, fine. We'll stop here. Thank you. Thank you all.